Okay, I guess I'll start. So let's just recap from Monday. Right, we started with a planar vector field C of class at least C1. Then after a little bit, we assumed that the expansion of the real field by C, so R bar is the real field, okay? We assumed that this is o-minimal. And from that, we extracted a certain cell decomposition definable in this structure, okay? So C is C1 cell decomposition of the plane, which is compatible with the set of singular points. Now that's pretty easy. But then with a few fairly basic arguments, we can make sure it satisfies the following two properties. One is that every cell in this decomposition is either tangent or transverse to C. Yeah, just to come back to a question I was asked at the end of the course, right? The way I defined tangent or transverse, I just defined it for a general immersed manifold, which doesn't quite make sense because a general immersed curve can have self-intersections. So I have to take that back, okay? But if a leaf of a vector field cannot have self-intersections. So for a leaf, it makes sense whether or not it's embedded or immersed. But then I started thinking again, do I even know one example of a leaf of a C1 vector field in the plane that is not embedded? And I don't. And in fact, I then convinced myself, and I leave for now as an exercise, that every leaf of a C1 vector field in the plane is an embedded manifold. Okay, so I leave that as an exercise. We can discuss this again during the question session. It's an interesting exercise. You have to use, I have to use at least, both the Jordan curve lemma or theorem and the flow box theorem for vector fields. Okay, just as a hint. Anyway, so yeah, to define tangent or transverse manifolds, right? I can restrict my definition from last time to embedded ones because I'm never applying it to anything else. The definable C1 cells are always embedded, and now so are actually the leaves that we're talking about. It's not true that the leaves of C1 vector field on any surface are always embedded. You can have a non-singular vector field on the torus, which has dense leaves. Okay, it's not very hard to construct. So those are not embedded. But that kind of thing can't happen in the plane. Anyway, let's get back to what else we did. Okay. So the other thing that we were guaranteeing by choosing the right cell decomposition is that for every open cell in this decomposition, which does not intersect the singular set, every leaf inside of it, right? So every leaf of C inside the cell is the graph of a function, that's a C1 function. L of C in C is the graph of a C1 function on an interval. Now, right, I had two possibilities last time. One was that it's a vertical segment, which of course is also the graph of a C1 function of the y coordinate, okay? And the other case was some graph of a C1 function of the x coordinate, defined on an open interval. Okay, so that's what we did. We showed how to do that, and we fixed such a decomposition. And from this decomposition, well, and the additional information, every leaf is linearly ordered by the direction of the vector field. So I use these orderings as well. Every leaf L of C is linearly ordered by the direction of the vector field, and that's usually denoted by less than L. Okay, so instead of saying I'm going forward in time, I just say it's greater than in this sense. All right, so with these pieces of information, right, we constructed what I call the forward progression map associated to this decomposition. So how did we do this again? One more thing that has room here, right? So we singled out those cells in our decomposition that are transverse to C. Right, so this can contain zero-dimensional cells that are not singular points. It will contain one-dimensional cells that are transverse. And that's it, right? Does not contain any open cells by our definition. Okay, and so with this data in mind, we defined the forward progression map. Okay, so where, okay, B is the set, the union of all transverse cells, together with an additional point at infinity that represents all the singular points for this vector field. Okay, and so F is defined from B into B. And the idea is that, right, such that if you have a point in B which does not get mapped to infinity, to a singular point, at point F of Z comes later on the same leaf as Z was. That's the idea, right? Both Z and F of Z lie on the same leaf. L of Xi, and F of Z becomes after Z. Okay. So I think that's where we more or less ended up, right? So yeah, I mean, maybe I didn't quite say why this is always well defined, right? You could think, couldn't it be that a point that's that lies on a transverse cell gets sent to itself because it's on a cycle. Why wouldn't that happen? Well, it can't happen because a cycle cannot lie in any single open cell because it's not a graph of a function. So any cycle does have to intersect B in at least one or more points, actually. Okay. Well, if it intersects B in at least one point, it will have to intersect again. So yeah, it's well defined, and it kind of codes, right, all these things. So what are the kinds of things that it codes? Well, we were interested in Dulac's problem. So what this map can code is the following kind of information. So let's say a point C in this set B, right? So in the in the domain of the function of the progression map is a fixed point of f. No, sorry, there are no fixed points of f, but it lies on a cycle of Xi. Well, what happens if it lies on a cycle? Right? Well, if it lies on a cycle, the first image is going to be another point on the same cycle, right? And the next point could be my original Z again, right? Or not, in which case it's yet another one. But eventually it will have to come back because a cycle is compact, right? And every time we map it to a new point, it can't accumulate, right? So it lies on a cycle if and only if some iterate of this regression map maps it to itself. Fn of z is equal to z. Right, and so Fn is just here the nth compositional iterate of f. Correct, yeah. So in fact, n greater than 1, yes. I don't even care too much about that now, but yes, we know it's at least 2. Okay. In fact, more is true. Right, so what this is saying is that for every point there is an n, da da da. But in fact, the other way around is also true. Okay. So there exists a single natural number n such that C in B lies on a cycle if and only if this nth iterate applied to Z is equal to Z. And that's because of what we proved on Monday, right? Remember, the pieces that make up B are all transverse to the vector field. So they will consist of 0-dimensional and 1-dimensional pieces. Okay, there are only finitely many of them. Okay. The 0-dimensional pieces can intersect the cycle in at most one point because they're only one point. The 1-dimensional pieces are transverse, so we proved they can intersect C in at most one point as well. So by lemma 1, if right, you can't map to a new point in B more than as many times as you have elements in the decomposition C trans. Okay, so there is an n between well, I guess 2 and the cardinality of C trans such that that iterate takes Z already back to Z. And now I have a uniform bound on that, right? The cardinality of C trans. So I guess I can take n to be the least common multiple of all these numbers, right? If I'm not mistaken, that should be enough. Right. That will cover all the fixed points of all the iterates between the second and the C transit iterate. Okay. Okay, so we have, in other words, F can define all the points in B for let me see, I want the notation to be right. I'm just going to look at each of these cells, right? So for each cell that's transverse, I can look at the set of fixed points of this F, of this iterate of F in C, right? So fixed, what is it? C, that's just the set of all Z. C, Fn of Z is equal to Z. Right, so this codes all the cycles that intersect C in a way, right? In this sense. Okay. Dirac's problem is not about cycles, it's about limit cycles. So now can I also define limit cycles? So again, right, B is made up of these transverse pieces. So for such a transverse piece, of course, if it's zero dimensional, well, there's only one point, right? Everything is dandy, right? There's only one cycle that can intersect it. But if the dimension of C is equal to 1, I can also linearly order C using the orthogonal vector field, right? Or just the fact that it's definable in this given o-minimal structure. So of course we can use the induced linear ordering on C from that way, right? Whatever, choose your favorite way to do it. Linearly order C, and that will be my ordering. Okay. So if I use this ordering as well, I can define what I mean by a limit, a point belonging to a limit cycle. So define, okay, here is fixed, isolated fixed point. So why not I fix of C, right? So that's now the set of all the in fixed, all those that belong to a cycle, but so that all nearby points with respect to this order topology are not on a cycle. So Z is isolated with respect to that topology in fixed C. Okay. Aha, so
excuse me.
yes.
Patrick, Fernando
Yes.
speaking. Yeah,
Yes,
it's what is the order induced in C, because C is transverse, is not
Right.
not a leaf.
So either I can use the orthogonal vector field to define the ordering, if that's what you like to do, or we can just use the induced ordering because it's definable in the o-minimal structure. Right, C is the graph of a definable C1 function on an interval. Just lift that ordering up. Make sense?
Okay, you choose one of those.
Yeah,
one of the two.
It all leads to the same linear ordering of.
No, Yeah,
of
okay.
the cell C. Okay.
No, it has nothing to do with the vector field, in fact.
No, no, you
not
don't
really.
need for it. No.
Okay. No. I was thinking if it was
You're right.
when you cut several times, you have an order induced by this cutting, because
Right. Yeah.
yeah.
I mean, again, in fact, Lau is right. He just mentioned that too. You could also just say in the induced topology from the plane on
Okay.
C. It's the
Yeah.
same. It's all the same topology.
Okay. Thank you. Yeah.
Yeah. Okay. So, right. So in other words, now we can say that Dulac's problem for Xi holds right if and only if each of these sets is finite. Right, so we're able to code Dulac's problem using some very simple definable sets in a certain very simple structure. Right, the structure I'm talking about, let this thing B, curly B, be the structure whose underlying set is B. Then I throw on every a predicate for every cell in C trans. Together with the ordering that I just used up there for every such cell. So you see, here I am forgetting that I'm in the plane, right? I have an abstract set B with certain predicates. That's why I wanted to introduce a name for this ordering or the topology that you have on there. Okay. What else did we use? F, yes, right, F. And the point that I guess, no, it's there, okay. We could introduce infinity as a separate constant point, but I don't think we need to. So this is an abstract structure, right? It's not, as it is, it's not linearly ordered, but there's a ordering in every piece of this universe if you want. We could make it linearly ordered in an artificial way if we wanted to, but and so in this structure here, we can define this set of isolated fixed points of F, okay? And we can code Dulac's problem. And it's a very simple set. It's a quantifier-free definable set. But in fact, and that's maybe the less trivial part, right? That I proved together with Alf Dolik a number of years ago. There is really nothing else to this structure. Okay, so what you might think, right? If you look at this set, if this set is all these sets are finite, it's like saying that the structure that I have here on each of the pieces of C trans is o-minimal. That's exactly the case. Okay, so Dulac's problem for C holds if and only if the structure, every C in C trans, of course, the points, right, that's trivial, so there's nothing to say there. C in C trans, the structure induced on C, on the cell C by this curly B is o-minimal. And really proving this just meant proving that we almost have quantifier elimination in this thing, right? We have to add a couple more things that are trivially definable true, and then prove quantifier elimination. What we need is the inverse of F, the backwards progression map. You need that in the language to prove it. Anyway, we proved a bit more too, so we also have a version of this theorem where you don't throw away the open cells. So if you also want to keep the open cells, you get, of course, a more complicated theory or seemingly more complicated theory, but you get a similar kind of characterization for that theory, although it's not o-minimal for obvious reasons. But anyway.
Can you sort of give a picture why if it's not, if Dulac's problem is not the whole, it's not o-minimal?
Well, if Dulac's problem does not hold, right, then you have infinitely many limit cycles, which means the intersection, one of these sets must be infinite and isolated and discrete. So it's not o-minimal. That direction is obvious, right? It's the other direction that's not so obvious, right? Yeah, so it's immediately seen on this set. Yeah. So you see, the reason why I wanted to tell this story is because, well, if you want to prove Dulac's problem for a certain vector field, right, you do that using the forward progression map by analyzing these sets here. Well, what this is suggesting that you do have to prove more than what it seems like. Right? It's very likely that this map is going to define an o-minimal structure, not just that it has finitely many fixed points, but as a consequence of all that, it actually has to be living in an o-minimal structure. So trying to prove this theorem, right, for a specific C by proving that this structure is o-minimal doesn't seem so far-fetched. It's actually a necessity, okay? Because, yeah, so far the proofs that we have for Dulac's problem, I will get to that, right, a little bit, don't go through o-minimality, and it seems like involving o-minimality in that seems like overkill, but what we are saying here is, no, it's not. Now, yes. Absolutely, right? So that the objection to that is we threw away all the structure, like in particular the field structure, the original field structure is all gone. Right? There's no algebraic structure on this thing other than the forward progression map. And that's a strange algebra. Okay, strange kind of algebra. And the reason why we did not include that is simply because it just got too complex, right? We thought, you know, we wanted to have one theorem. This was already a theorem of, I don't know, 30-something pages. And so we thought, you know, how interesting is that going to be if it's going to be 130 pages, because we also show we can do it with the original structure. And I don't know if we can, right? We haven't tried, although Christian Delbey, I had a brief discussion with him, and there are some recent results about stably embedded sets in certain structures that suggest maybe what we did could actually be done while keeping the original induced structure on B. I don't know. I haven't done it. So that's the objection to the question of o-minimality might still be overkill, but at least not as much as one might think at first. All right. So let's see, what else I want to say about this. Oh, yes, right. And so that's really, in this generality, that's really all we can say. I mean, there's no, we don't actually know what the nature of this map is other than this. Okay, again, right here we proved this theorem, but by forgetting all the other structure that was around before. So if you just have a real line with a function, right, you can actually get o-minimality quite quick. So this is not, in that sense, maybe not that surprising. So from these maps, right, I want to retain, we'll go back to that picture that we had up last time. So here's a cell, one of those open cells, where we had, say, a singular point maybe down here. I think we had, yeah, I want to draw kind of the same picture that we had last time, right? Two tangent cells. It's just to right, and so this is a singular point. And all the others are not in transverse, the white ones. And then we had kind of the flow of the vector field looking like something like this. So all these leaves are graphs of functions, but they get steeper and steeper and steeper as you approach the left end. Okay. And so in a situation like this, right, every point here gets mapped to a point over here. There's no other choice. Okay. And then this guy might be singular or not. We don't know that at this point. So, right, but you could have a slightly different picture. It's not quite as straightforward in a situation where, so let me draw another one. And I'm trying not to, so it could have a similar cell, but not the same tangency conditions, right? We could again have a singular point here, say, but and maybe only this one here tangent, and all the others transverse, right? So then you have some leaves that come in here and then exit somewhere over here, say, right? But then there's one here that will also have to exit over here. Yes, and so on, right? Okay, so what happens in this case is that if I look at the image of just this cell here under the map F, over here I get a subinterval. Okay. From here I get the point, and then from here I get the remaining subinterval. So right, it's not always just from one to the other. Okay. But so what you can always, right, fairly easily show from our definitions is that F always maps intervals in disordered topologies to intervals, right? So fact. For every C and C prime, two cells in C trans. And now it may be, right, for an arbitrary pair, F might not map any point of C to anywhere in C prime. So then it's, right, that's okay. But the restriction of F to C maps intervals to intervals. In other words, it's continuous. One way to say it, right? Which means that you can find maximal subintervals, possibly empty, I of C and I prime of C prime such that if the whole image is I prime and the restriction to I to I prime, well, is bijective, order isomorphic, right? An order isomorphism, so something like that.
Might not. There are also points that see that it might not map to C prime at all.
Yeah, exactly. So it might be empty. So the
You notice FC is I prime, so I suppose you mean F, the inverse image of I prime is all of I or something like that.
yes, well, yeah. So I prime can be empty, right?
If you wrote FC is I prime, which suggests that F maps all of C into C prime. Which is not what you mean.
Oh, I see what you mean. Yeah. Okay, sorry. Yes. Okay. Yes. Yeah. There we go. Is that better?
Patrick, sorry, on Zoom we can't hear anything now. Like we could hear until 30 seconds ago. Something has changed. Nope, still nothing. Nope, nothing.
Right.
Yeah, we can hear now.
Hello. Can you hear me?
Yes, now we can hear.
That's that too. Okay. All right. Okay, you can hear me now?
Yes, it's fine. Thanks.
Excellent. Okay, so these maps here, right, I'm going to call, well, the correspondence maps. Where is it? Oh, here, right. So these maps FCC prime are the correspondence maps. They describe, so to say, the local behavior inside one of the open cells. Okay, and the thing is that the graph of F is the union of the graph of these guys together with the graph of the of the portion of f that sends points to infinity, right? So the pre-image of infinity that's separate from all of these, right? But of course that's a trivial map, right? So which means if you want to prove o-minimality for f, right, all you have to do is prove o-minimality for each of these guys, for example. Okay, and that's actually kind of the strategy that people use to prove Dulac's map, Dulac's problem in particular cases. So I still have 10 minutes, so let me start a little bit with what's actually known at this point. Yeah. So like I said, this is all that we can say at this point in this generality. Right. If we are given a vector field that's definable in a no-minimal structure, okay, I can construct the cell decomposition definably. I can define this map F, but I have no idea what nature the map F has. Right. The only thing I know is this. After throwing away all the underlying structure that we started out with, this map has certain properties that are nice, okay? But what is actually the nature of this, right? So if you want to prove Dulac's problem, we have to actually somehow have additional methods to analyze F. Right? And the only methods I know at this point are analytic in nature. So from now on, right, we focus on the known case of Dulac's problem. Where C has a real analytic extension, so it's not just real analytic, but has a real analytic extension on S2. In other words, one point at infinity has to be included in the picture, okay? And it has to be real analytic there as well. So in this situation, right, C is actually definable in a no-minimal structure, or sub n. And so we can do this whole cell decomposition business. We just do it in the plane and then add one more singleton point to either C the singular set or C trans, whichever it's ending up being. Okay. So in this case, we add, right? So S2, right? I'm just going to consider as R2 together with the pole at the North Pole, P. Okay, one point there. I don't want to call it infinity because I used the infinity here as the singular set, coding the singular points. So in this case, we just add the singleton P to C, right? Whether it's tangent or transverse, depends on the vector field. Everything else stays the same. Okay, so so in this case, right, what people actually do to prove Dulac's problem is to look at these correspondence maps. Okay, that's exactly what they do. And they are trying to, well, not quite prove o-minimality. that was not the goal in this first page, in these cases. So, so in this situation, let's say we are, in this picture here, right? The first thing that's true in addition to what we had before is that So like in this picture, we have f from C to C, from I to I prime, right? That's one of those correspondence maps. If I restrict it to any proper subinterval, closed subinterval of I on this side, right? Then that means the image is going to be a proper closed subinterval of I prime. Okay. In this case, the map F C C prime restricted to, well, okay, this blue subinterval, what should I call it? J. Okay. Restricted to J is definable in R sub n. That's a strong property that in this general setting, we have no idea. Okay, so why is this? So if J in I prime is compact, that is because of the theorem about ODEs, which says that dependence of solutions to ODEs of a certain smoothness is equally smooth on the parameters. Okay, so for example, in this situation, we have real analytic vector field. So we have real analytic ODEs that we are solving to describe the flow. And the theorem of the theory of ODEs tells us that the solution, the flow, depends real analytically on the initial conditions. In other words, like here, you can consider the blue interval J to be a set of initial conditions for the flow, which you follow. And then the entire flow is going to be real analytic too. In fact, because we are on a compact interval, it will be restricted real analytic, and therefore definable in R sub n. So that's only true for that we only know this for real analytic. Okay, yes? No, not at all. No. So, right, this is every single leaf is definable in the Pfaffi enclosure, but the flow from an entire interval, that's much more. That's like a family of leaves, and that's not definable in the Pfaffi enclosure. So we do not know anything about definability of, even for this restricted situation, in any o-minimal expansion that I'm aware of. Okay. We do know it here, not because of any Pfaffi enclosure business, but simply because of analytic dependence on initial conditions of solutions. And so when we restrict to compact intervals, it becomes restricted real analytic and therefore definable in R sub n. We have no idea otherwise why this is the case. Right? It's not because it's Pfaffian, it's because it is not. Okay, so that's this is very important for the real analytic case. This is true, which means we really only need to worry about the germ of our maps, our correspondence maps near the singularity. That's really all that we need to worry about. So, right, all we need to worry about is some remaining interval here and its corresponding image over here. Arbitrarily small is okay, as long as it's not zero. Okay, so that's going to be one of the strategies. So because of this, right, in the real analytic case, we only need to, and only here, I'm going to put this in quotes, okay, to understand, because we already understand the other parts, the germs of the correspondence maps. Near singular points. And this also needs to be, I want to make that a little bit clearer, and then I'll stop for today. Near singular points. So what do I mean by this specifically? I mean, in this picture, it's literally near the singular red point, but this doesn't have to be the case. Yeah, no, that's not okay. Here, in this picture, what does it mean to say near the singular point? Here we have only one correspondence map, the one that maps things here to here, but the singular point is down here. So what I mean, right? Of course, the closer you start to the blue line, the more you go down here first before you go over there. So near the singular point means actually the germ here, which gets mapped to the germ here. Okay. So it's this piece that we need to understand when I mean near the singular point. So let me make that a little clearer. Yeah, and then I'll stop. It's just one more picture or definition, I guess, sorry. So we are going to introduce, in this case, I guess, real analytic coordinates. X from an interval 0 epsilon to I, right? Where is I? Oh, I is here. I is on the top. Okay, and another one, y from 0 delta to I prime, which is this guy over here. Such that x of 0 is a frontier point of my cell C, of the interval I. Left or right endpoint of the interval I. Okay. Y of 0 is the corresponding frontier point. Well, corresponding, I don't know what that means, right? Because, but it's a frontier point. And such that well, the image of X is the orange interval on the top, and the other one is the orange interval at the right bottom. In other words, what do we see? If I look at a point X of t, that's in the orange interval, I apply my F to it, I get a point in the other orange interval, and that should be Y of t. Okay. So I've, in other words, using these definable coordinates, right? I changed the problem into a problem of germs of real functions. In this case, I guess real, yeah, these functions are even real analytic, just not at 0, right? So I'm looking at the germ of this function now, GC prime, CC prime, where GCC prime is the function that's pulled back from via these coordinates from F. So of t is equal to y inverse of F of X of t. Does that make sense? Right, so I've translated the germ between these two of f between these two orange intervals into a germ at 0 plus of a real function. Okay. So this is the kind of thing we end up studying, germs of functions like that. Okay, so that's what I'll start doing next week for a real analytic case. Well, yes. Any questions? All right. So I wanted to say one thing. I am also typing up some notes, and they can be found on my webpage at McMaster. I have already asked them to post a link, but it hasn't happened yet. So if you go to my webpage at McMaster, to my not the official one, but my webpage, you look under teaching. There is something called fields module, and under the fields module, you will see entries that summarize what I'm teaching here. So I've already written one for Monday, and I haven't written one yet for today, but I will. Okay.